morning, everyone. It's my pleasure to have the honor of introducing our speaker today, DTM's very own Larry Nittler. I ran across Larry the first time in the early 90s when he was giving talks at the Lunar and Planetary Science Conference meetings in Houston, maybe a few WashU, Clemson University workshops here or there, and beyond. And I was really impressed with his work, and I thought, wow, this guy's really good. I think he must be some research professor or academic professor at WashU. So finally, after one of his talks, I went up to him and said, hey, so do you get a lot of time for research? Are you mostly teaching classes these days or what? And he says, well, actually, I got a lot of time for research because I'm still a graduate student. It was pretty impressive. So I missed the mark on that one pretty badly. But that's all for the good because it meant that we could hopefully, sometimes bring him to DTM. So sure enough, in '96 when he got his degree, he came here as a postdoc. But he had previously gone to Cornell and got his undergraduate degree there in physics. Then he went to Washington University to do his Ph.D. with Bob Walker, who was one of the pioneers of applying physics and radiation physics to meteoritics, which is a wonderful advance. And so he was involved in Bob Walker's group involving looking for presolar dust grains, which is what Larry will be telling us about today, about the wonderful things Larry's done on that point of view. While he was there, actually, at WashU, our own Connell Alexander was a postdoc there. So I think the forces were in play for when Larry was looking for a postdoc. In '96, he came to DTM as a Carnegie fellow for 3 years, where he did some fantastic stuff, obviously, because we've hired him. So you'll find out more from the talk today, too. And but when all good things come to an end, and so when his postdoc was drawing to a close, he applied for and got a job at NASA Goddard Space Flight Center, close by. And shortly after that, he accepted that job and began work there. He was also offered a job here at DTM as a permanent staff member because there were openings planned or already available. And Larry said, well, fine, but I think I really should go to Goddard and learn some things about managing space missions. And so he had work to deal with John Solomon to go to Goddard for a couple of years. And because of the fact that DTM and John Solomon at that point essentially had a funded but unfilled position for a couple of years, when I marched into Sean's office at one point and said, we've got to hire Paul Butler, no one realizes what a gem he is, Sean said, yeah, let's hire him. So we were able to hire Paul Butler, thanks to Larry Nittler. So hats off to you, we are not worthy. Fantastic stuff. Yes. And then when 2 years later, Larry left Goddard and came here as a staff member, where he's been happily ever since. So, at least I hope so. We'll find out today.
This place is all right.
Okay, except for the week you're cooking for lunch club, then things are pretty grim. Well, I'll let the eating audience respond to the rest of that. But anyway, Larry is a prize winner. He won the Alfred Meir Award, which is the Young Person's Prize for Meteoritical Society. He's also a fellow of the Meteoritical Society. And of course, given also his experience with at Goddard as a mission manager, he became the deputy PI of the Mercury Messenger mission for a number of years once Sean Solomon left us. And so he's played several roles there. So there he's talking about an object which is 10 to the 6th meters in size. We're going to go down total orders of magnitude today, go to micron size, and Larry's going to tell us about presolar dust grains. Thank you.
Thank you, Alan. That was quite an introduction. What? Thanks a lot, Alan. The last time I gave a seminar in this room was talking about Mercury, because a few years ago from the Messenger mission. And as I tell people, my research is sort of bifurcated between measuring elemental abundances on a 100-kilometer scale and measuring isotopes on a submicron scale, and I don't really do a lot in between. But so today's on the micron scale things, except that I study things, I'm going to talk about things like this, which is a micron-sized little ball of carbon extracted from a meteorite. But the point is, even though this is small, we use it to derive information about things like this, which is very, very large. This is the Cassiopeia A supernova remnant. And we have good reasons to believe, as I'll talk throughout the next 45 minutes or so, that grains like this originated in these kinds of environments. And we can use laboratory analysis of things like this to learn a lot more about stars and supernovae and other astrophysical phenomena. So this is a cartoon of the basic idea, and the basic idea is that 4.5 billion years ago, part of a molecular cloud in interstellar space collapsed to form the protoplanetary disk that became our solar system. part of the material in this molecular cloud were pre-existing dust grains that had condensed in cooling winds from late evolved stars and supernova ejecta and got mixed up with other dust and gas in the interstellar medium. And when this cloud collapsed to form the protoplanetary disk, some of these dust grains survived in the initial planetesimals that never formed full planets and comets and asteroids that remained small enough that they never underwent geological processing and are essentially fossil remnants of the disk phase of our solar system evolution. We've now known for almost 20 years that the, 30 years. Next year will be the 30th anniversary of the discovery of these grains. That when we look at samples of meteorites, of asteroids and comets that come to Earth in the form of meteorites or interplanetary dust particles, or now increasingly material returned by spacecraft, we can actually take these apart and find these little grains and identify that these were some of these primordial stellar dust grains, stardust, that has existed for a very, very long time, that are older than the solar system. So we call them presolar grains, or circumstellar grains, or stardust, or some combination of all those words. They were interstellar grains for some period of time before the formation of the sun. So it's a way of doing astronomy in the laboratory, not astrophysics so much, but astronomy, because it's an observational science, which you can then, of course, do astrophysics. Someone can tell me what journal they should be in now that I hear chortling from the astronomers. I should mention these are very rare. They're typically in the order of less than 100 parts per million of these rocks. So most of the material in this molecular cloud got heated and homogenized during the formation of the solar system, and it's only a very small fraction of the stuff survived. But as you see, we can do a great deal with these things now. So of course the first question people always have is how do you know that? How do you know these things predate the solar system? And the answer is from the isotopes. So these are diagrams showing the isotopic composition of carbon and oxygen in the solar system. And basically, on a scale with these many orders of magnitude, almost everything in the solar system is a delta function on this histogram. There's about 89 carbon-12 atoms for every carbon-13 atom. Now there's percent variations around that are extremely important scientifically, and people like Marilyn Vogel have spent her career looking at small variations in carbon isotopes to track various biological processes on the Earth. But on the scale of this plot, it's all about the same, percent variation. Similarly, almost everything in the solar system has the same oxygen isotope composition, within maybe plus or minus 5–10%. We know that planets are about 5% different than the sun, but again, with orders of magnitude variations, that doesn't really matter. Now, if I plot these dust grains on the same scales, we can see a very, very different picture. So instead of 89 carbon-12 to carbon-13 atoms, if we find a silicon carbide grain, a little micron piece of silicon carbide, it might have a ratio of 3, or it might have a ratio of 10,000. And almost anything in between, but not almost anything. There's obviously clustering. We have a histogram here of well-defined peaks and so on. And similarly, for the oxygen isotopes, instead of all being 10% around these lines, we have a range. We have to plot on a log scale these isotopic variations. So these are not subtle isotopic effects. They are they're far more extreme than anything else we see in the solar system, and they're way too large to explain by normal sort of chemical, physical fractionation processes. Photosynthesis or diffusion or evaporation or whatever. They really require nuclear processes. These are the only physical reaction processes that can fractionate the isotopes to such an extreme degree. And this immediately points to an origin in the place in nature where you have large amounts of nuclear reactions going on, which is in the deep interiors of stars, since nuclear reactions are what power stars in the universe. So, and in fact, we can compare, on these particular isotope diagrams, we can actually compare with astronomical observations. For some for some stars and some isotopic systems, you can do spectroscopy and for isotopic ratios of environments. And for example, this has been done now for carbon-rich stars. These are carbon-rich red giant stars, evolved stars. And what you find is that the distribution looks remarkably similar to the silicon carbide grains. Similarly, for the oxygen isotopes, oxygen-rich red giant stars have overlapped very well with the grain data we see. So this immediately gives strong support that these grains formed in stars. So these are some, as I said, these have been now known for about 30 years, and I'm going to talk about some overview stuff, but try to focus on some recent work and interesting discoveries from our group and various postdocs that have been in our lab for the last few years. These are some images going back a while these are all made with electron microscopes of some of these dust grains. So some of them are little tiny crystals. That's a 1 micron scale bar, so this is a few microns across. Crystals of silicon carbide, graphite grains. If you slice the graphite grains and look at them in the transmission electron microscope, they often have subgrains. This is a little very, very small titanium carbide crystal on which this graphite accreted in the outflow of probably a supernova. We see glasses, we see other minerals of oxides and silicates. We see diamonds that are 2 nanometers across. These are a little more ambiguous. I'm not going to talk more about the diamonds. But the point is there's a very wide range of types of these grains have now been identified. And a key point is that these grains condensed from stellar matter at a specific time and a specific place in a star. So it's a fossil record of the nucleosynthesis processes that affected that bit of gas at that time in a star. By studying these in the lab, we can get very detailed information about stellar and interstellar and early solar system processes, and I'll give examples of these throughout the talk. This whole field is made possible by the fact that people like computers and things. So there's been an enormous advances in nanoscience and nanotechnology and instrumentation for studying things on smaller and smaller scales. And it turns out things that are designed for analyzing silicon wafers for the semiconductor industry can also be used very, very well for studying presolar grains. And of course, some of the instruments are also optimized and developed directly for science and not technology. But the point is that modern techniques now allow us to do very, very interesting things with these grains, and it's getting better and better. So these are, I said this is astronomy in the lab, so these are our telescopes. This is a picture of the nanosims in the basement of the cyclotron building over there. This is the main tool I've used in my career to study these grains, and this basically is secondary ion mass spectrometry, where you take a solid sample, you focus a beam of ions, either cesium or oxygen, onto it, it knocks atoms off, they get ionized, and you can put them through a magnetic sector mass spectrometer and weigh them. And this allows you to measure major and minor element ratios in grains bigger than about 100 nanometers. There's very interesting work, largely at the University of Chicago, with resonance ionization mass spectrometry. This was a technique that was pioneered in part here at DTM in the 80s, and then abandoned for the applications that we're interested in here. And in the last 15, 20 years, it's been revitalized in Chicago, largely for presolar grain work. And basically, you use a laser to knock atoms off your sample, and you shine other lasers through that little cloud of atoms with the wavelength of the light precisely tuned to ionize only atoms of a single element you're interested in. And this allows very, very sensitive mass spectrometry of very, very low abundance elements in these grains. And this is a fabulous new instrument being developed by Andrew Davis at the University of Chicago called Chile. The previous instrument was called Charisma, and Nan Luth did her Ph.D. work on this. I'll show a little bit of that later. So this is very cool. And in addition to isotopes, electron microscopy is an extremely important tool for studying these grains because it allows you to do a very, very tiny scale mineralogy on these grains. You can learn their structures, their composition on the nanometer scale. And this is an exciting new instrument that Rhonda Stroud has at the Naval Research Lab now called the Neon Ultrastem that allows X-ray detection of single atoms. So how do we find these grains? The classic technique and the way they were discovered is by a thing that Ed Anders developed and termed burning down the haystack to find the needle. And the basic idea is that starting in the 60s, it was discovered that there were noble gas, isotopically anomalous noble gases in primitive meteorites. And they had to be carried in some very tough phase, and decided they might be presolar grains. And Ed Anders and his colleagues spent the next 20 years basically experimenting by taking meteorites, sticking them in acid, dissolving away a lot of material, looking at the residue. Does it have more or less of that noble gas anomalies? If it has more, hit it with another acid. And after 20 years, they successfully did this. They did a whole series of chemical treatments on the meteorite, ended up with a residue that was things like silicon carbide and aluminum oxide, these very, very tough acid-resistant phases. And at the same time, the ion probe was being developed. The SIMS technique was being developed by Ernst Zinner at Washington University. And he looked at these silicon carbide grains and saw the plot I showed a few slides ago, that these grains had carbon isotopes completely insane compared to anything else in the solar system. So this is a good way to find presolar grains that are acid resistant. We now know they're there. We can still try different techniques. But further advances in technology, in particular the development of the nanosims, now allow us to find these things in situ in the meteorites without burning down the haystack. And this is very important if you're interested in presolar hay. For example, silicates, which are the most common type of dust in the universe. We were throwing all those away with the haystack when we burned this down, because the first thing we did with this is get rid of all the silicates. So we can find presolar silicates by in situ mapping, and these are little nanosim squares where we've used the nanosims to make little isotope maps, 10 micron by 10 micron, and we can go over and over again. It takes a couple days. And you can do this in different isotopes, and you can zoom in. And for example, this is one of these little squares. When you look at the 17 to 16 oxygen isotope ratio, lo and behold, there's a little 200 nanometer diameter grain that has a factor of 2 excess in oxygen 17. So this is how we can find these grains. These grains, by their very survival, the fact that they preserve these stellar isotope signatures tells us that they are extremely pristine, because almost any process that could have affected them would likely have erased their isotope signatures, and we wouldn't recognize them anymore. So they're witnesses to a large number of processes throughout their long histories, and they've been used for a number of different scientific investigations in cosmology and a lot of astrophysics, as I'll get into later, as well as, we can investigate what happens to dust in their stellar medium, as well as understand what are the sources of material for the solar system and some processes in the early solar system. And I'm going to touch on a lot of these. I probably have too much, but we'll see. So in terms of sources, we now, after all these years, have a pretty good handle on most of the grains. So the large majority of the grains formed in either asymptotic giant branch stars or type 2 supernovae. A very small fraction might have formed in novae, and I'll talk about that later. And some of the grains we don't know the origin of, but most of the grains formed in these types of stars, which makes sense because from astronomical observations, these are also the stars that are estimated to be the major producers of dust in the Milky Way today. And I'll talk about what these stars are. For example, a little digression into stellar evolution for the non-astro-oriented people here. Recall that stars evolve. Stars basically are in hydrostatic equilibrium because they're producing energy from nuclear reactions deep in their core. And so the sun right now is a main sequence star burning hydrogen to helium happily. Eventually it's going to run out of hydrogen in its core. It's going to completely convert to helium, at which point the fusion reactions will stop. It will quit producing energy and radiation to balance the gravitational collapse, and essentially become a red giant and start burning helium, and then eventually starts burning helium to carbon in its core, becomes a red giant. It then becomes what's called an asymptotic giant branch star, which is still burning helium to carbon, but at this point in a shell. And eventually it blows off its envelope and becomes a white dwarf with a planetary nebula around it. The nebula will disperse and you'll have a cooling white dwarf for the rest of time. This is a schematic structure of the IDP star. As I said, this is where we think most of these grains form. At this point you have an electron degenerate carbon and oxygen core, will eventually be the white dwarf. On top of it is a thin shell of helium that burns, a thin shell of hydrogen that burns, an inner shell region, and then a very, very large convective envelope. And this envelope is fully convective, and it's cooling as you get farther and farther from the center of the star and gets to the temperature that dust grains can condense directly out of the gas, and then radiation pressure on the dust can drive a stellar wind. And these are seen to be they're seen to have dust and to have very strong winds. The key point here is that you have, in these nuclear burning shells, you have helium burning to carbon. So you're making a very, very carbon-rich layer. And this is also where the S process is happening, which is a nucleosynthetic process that makes about half of the heavy elements in the periodic table. And it's S for slow neutron capture. So basically there are reactions going on in here that release neutrons, and then they can be captured by heavy elements to make heavier elements. Periodically during the evolution, there's mixing episodes that mix material from deep inside to the envelope, which, as I said, is convective. So you mix a little bit of this carbon and S process here, it then gets mixed throughout and becomes part of the dust grain. So these mixing, although the nucleosynthesis doesn't really happen in the envelope, you get nucleosynthetic effects in the envelope because material that has been burned by nuclear reactions gets mixed out. And we'll see this. In terms of the dust grains themselves, from infrared astronomy, we know there's dust forming in these stars. And we know that it depends critically on the bulk chemistry of the star, and in particular the carbon to oxygen ratio. When you have less carbon than oxygen, the carbon is all locked up in CO, carbon monoxide, which is an extremely stable molecule. So you have extra oxygen to form dust, and so you form things like silicates and oxides. When you have more carbon than oxygen, which happens as you gradually mix this carbon from the helium shell into the envelope, you change the chemistry drastically. And you can see this. In an oxygen-rich star, you have features from silicates, and in carbon-rich stars, you have features from silicon carbide. And this is critical to understanding the grain data we have. So I'm going to talk a little bit about the carbon-rich grains and then the oxygen-rich grains on AGB stars. As I said, more than 90% of the silicon carbide grains come from AGB stars, and maybe half of these graphite grains, which are not pure graphite, they're generally poorly graphitized or partially graphitized carbon. Some are amorphous, some are pretty well graphitized. These I've already shown this slide, but the fact that we think most of the grains came from AGB stars is largely from this match in the carbon isotope distribution, as well as the observation that you have silicon carbide forming in these stars. But in fact, when we go into detail on the nitrogen isotopes, the silicon isotopes, the magnesium isotopes, everything makes sense. And so we now have a very good handle on that these grains formed in AGB stars. And one of the biggest, I think, most important results from this whole field has come from these resonance ionization mass spectrometry of these grains. And this is an old plot of molybdenum isotopes measured with the old Charisma instrument in Chicago. That these are molybdenum isotopes measured in individual silicon carbide grains. And the red points are the grains. And these are predictions from detailed stellar evolution models of nucleosynthesis of molybdenum and zirconium isotopes in AGB stars. And what you see is, in most of these cases, an extremely good match from the grains to the models. This is further evidence that these grains really did form in these kinds of stars. It's also profoundly important because it's among the first confirmation that the S process really exists in nature. The S process was determined to exist by a mathematical deconvolution of the solar abundance pattern back in the 1950s. And it works beautifully from a nucleosynthesis point of view. But there wasn't direct evidence until presolar grains that you actually had a distinct S process component in nature. And this proves it without a doubt. We can, of course, then also use these data to better understand the models. When there's deviations, small deviations from the models or large deviations from the models, or different models of different parameters make different predictions, you can actually help better understand the nucleosynthesis that occurs in these stars. And there's also interesting cases like this, where you see there's actually in this particular case, there's a large discrepancy between the models and the grains. And this was noticed, and it was suggested that maybe it was a problem with the models, but not the stellar models, but with the nuclear physics input, and the idea that there could be a cross-section that was being used in the models that was wrong. And a few years ago, this is, quite a while ago now, almost 8 years ago, this observation motivated a nuclear physics measurement, and they remeasured the reaction rate, found that the reaction rate was higher than had been previously thought, and when you recalculate this with the new reaction rate, you get perfect agreement. So this is a case where measuring a rare element isotope composition of a microscopic dust grain that's present at 10 parts per million in a meteorite told nuclear physicists that they needed to measure something and found that it was wrong. So this is cool connections all over the place in this field. More recently, just to say, because that was old, this is now from Nan's Ph.D. thesis, and she gave a seminar on this on her work last year. And I don't want to get into any details except to say they've really pushed the technique with the RIMS and measuring various elements and isotopes, and can really do serious constraints on the models, and are using the grains to get a much better handle on how the nucleosynthesis occurs in these stars. There are important free parameters in the models, and if the grains can help us figure out what these values are, it might get us to a better physical understanding of exactly the detailed processes going on, because you still can't solve an AGB star in 3 dimensions from first principles and get everything right. So jumping to the oxygen-rich grains, again, this is a plot I showed earlier. We have this huge range in oxygen isotopes in these individual grains. As I said before, that when we compare to the stellar observations, they seem to agree with the oxygen-rich AGB stars, at least most of the large majority of the grains which are in this region. And in fact, they also agree very much with predictions for AGB models. So we know that about at least 80% of these grains come from AGB stars, and it's not just the oxygen and other elements as well, and I'll get to that in a second. Point to an AGB source. Let's see what's next. Yeah, so for example, we can measure other elements, not just the major elements. That's one of the beauties of these kinds of studies, is that when you have the grain in the lab, if you're lucky and you have good instrumentation, you can measure lots of elements in the same grain, and that puts a lot of constraints on the specific source for a given grain. And you can measure things you cannot measure spectroscopically. So there's a way to get at data that's astronomically important without, for which there's no other method to do it. So for example, it turns out when we look at these oxide grains, these are aluminum-rich micron scale oxide grains from meteorites, we find a huge range of magnesium-26 to magnesium-24, which is clearly due to the radioactive decay of aluminum-26, which I don't have written there, which has a mean life of 1 million years. So it means when these grains formed, they condensed with aluminum-26 that has subsequently decayed to magnesium-26. From plots like this, you can figure out how much aluminum-26, and you can see these grains have, in some of these cases, the grains have almost 10% of their aluminum was aluminum-26 when it formed. Well, if the grain is aluminum oxide, that's half the grains are aluminum, so that tells you that something like 5% of the atoms in this grain were radioactive when it formed. Stars are kind of cool places. Similarly, some of these grains have calcium-rich oxides. We measured the potassium isotopes in them and found large excesses in potassium-41, which turns out is the decay product of calcium-41, which is also produced from AGB stars, and also has a short half-life of, I don't know, hundreds of thousands of years. And I can't remember now. The point is that, again, we can derive how much calcium-41 and aluminum-26 was in these grains when they formed, and then we can compare these to the models. And so here's like the derived calcium and aluminum with the models, and we can see in cases where the models agree and where they don't, which tells us something about our understanding of the stars. I want to talk briefly about this group of grains, which I didn't discuss a second ago. So as I said, these grains, we clearly come from AGB stars. We have thought for years that these also come from AGB stars, and I still think this. But their origin has been mysterious since we first discovered them in the early 90s. And they're very, very poor in oxygen-18. So something has destroyed their oxygen-18. This is a signature of hydrogen burning by the so-called CNO cycles, which is a series of catalytic nuclear reactions that happen during hydrogen burning. But it's clear something has to be destroying the oxygen-18 in the envelope itself. You can't just mix material from the core to the envelope and get to these compositions. So it was starting in like 1994 or 5 when we discovered these grains, it was immediately recognized there were two possible explanations. One is something called hot bottom burning, which I always liked. And the point is that in a massive AGB star, say more than 4 times the mass of the sun, during their evolution, the base of the envelope gets so hot that it starts burning hydrogen directly. So this is one case where you actually have nucleosynthesis happening in the envelope. So this very quickly destroys all the O18, makes them O17, and so on. It also keeps the star from becoming carbon-rich, because as the carbon gets dredged up from the interior, it gets burned to oxygen again. The other option was cool bottom processing, which was thought to occur in much smaller AGB stars, and this is also called extra mixing. And this is not that it was thought to happen, but that if it happened, if some magical mixing occurred that's not predicted by the standard hydrodynamic models, then you could instead mix the material slightly deeper, heat it, and mix it back to the surface. And in fact, for 20 years, we have favored this. And the reason was that all of the models of hot bottom burning predicted 17 to 16 ratios too high for the grains. They couldn't explain it. And there's been a lot of work on the cool bottom processing models, lots of papers for many, many years. And for years, I've given this talk and said, and these grains tell us that this process happens in stars. Well, now I'm showing you hot off the press data, a paper we're working on. And this is that a brand new paper is coming out in PhysRev Letters of a new measurement of a key reaction rate, the proton destruction of oxygen-17 with release of an alpha particle and nitrogen-14. This is a key reaction rate in hydrogen burning by the CNO cycle. And they've got a lab in Italy was able to do this measurement underground with much lower backgrounds, and we're able to measure it at the actual stellar energies, which is very unusual in nuclear astrophysics. Usually it's hard to get to the same lower. Usually the energies you can measure these reactions in the lab are higher than where it's actually happening in the stars. And what this rate, this is the best measurement ever of this rate, find that the rate is much higher. The more 17 is destroyed more easily in hydrogen burning than before. And so these are hot bottom burning calculations with the old rate. And as you can see, these are the grains. And this is where all the models predicted the grains should be. And now with the new rate, this is where the models predict the grains should be. That still doesn't match the grains because the grains have a little bit of oxygen 18. But in fact, the difference between this and this is not very much in terms of these measurements. It's, the grains at the lowest end here, in fact, are generally upper limits on the oxygen 18, that a few atoms of terrestrial contamination could have moved you from here to here in the measurement. And in fact, but not all of the grains. And in fact, so this is now showing if we mix this new material with solar by some mechanism, we can actually explain the data. So this is a paper we're working on. It changes the whole paradigm of what we've been doing for years on these grains. It's pretty interesting. It really implies that a much larger fraction of presolar grains are from massive AGB stars than we thought before. In fact, we thought before we didn't have any grains from there, and now we might have 10, 20% of them. It still has, you have to explain this mixing. There's a lot of details we haven't worked out. But this is much more consistent with what's expected. There was a nice paper from Gale and colleagues a few years ago that did a very comprehensive model of galactic chemical evolution and included dust formation and dust destruction and predicted that half the grains, pre-solar grains from AGB stars that would have been present at the time of the solar system should have been from massive AGB stars, and we found 0. And so perhaps we didn't find 0, we've just been using the wrong nuclear physics. So unfortunately, this field is a little bit, it's iterative in that we depend on the models to understand where these grains come from, and then we can constrain the models. But garbage in, garbage out, if the models have the wrong nuclear physics, then they're going to make the wrong predictions. And so before I showed a case where the grains pointed to an error in nuclear physics. Now this is a case where an error in nuclear physics was found and it pointed to an error in the models and in the interpretation. So it's an example of how this science works. There's also a lot of, we can also get information not just from the isotopes, but from the mineralogy. And this is work pioneered by Rhonda Stroud at NRL to use the focused ion beam. And we have, of course, this capability now on campus, which uses a focused beam of gallium ions to extract very, very small sections of material. And so here you can find the presolar silicate by the nanosims, use the focused ion beam to cut out a 100 nanometer or 50 nanometer thick slice of it out of the meteorite, and then look at it in the transmission electron microscope. And this has now been done for 20 or 30 presolar silicate grains, and we find a huge range of different structures. They're heterogeneous. This is a presolar grain that has huge variations in the magnesium and silicon content on a 10 or 20 nanometer scale. This is a calcium-rich and aluminum-rich presolar grain. This is a grain that has enstatite, pyroxene composition, but the microstructure is a high-pressure phase, a perovskite phase, which makes no sense for a grain that condensed in a low-pressure environment. So we don't understand this at all, but it tells us that that dust formation in stars and processing in interstellar medium is complicated. Probably a lot of non-equilibrium processing. And now this is some very interesting work that Aki Takegawa did a couple years ago when she was here, and the paper is now close to completion. She looked at presolar oxide grains, found a lot of these aluminum oxide grains, did the Fib work, did TEM with Rhonda, and these are two very interesting grains. This is them before they were sliced, and this is them in the TEM. And what you can see is when you look at them in the TEM slice, this one has giant cracks going through it. This one has a little micro impact crater. We think we're looking at direct evidence of interstellar dust processing in the interstellar medium. Astronomers and astrophysicists for years have made models of dust processing in the interstellar medium. And the most common way to destroy grains, we know grains are destroyed in the interstellar medium, is to basically have them accelerated by supernova shocks that smash into each other and break apart. And we think we have direct evidence for this. That's cool. So now I want to talk about the supernova grains. Okay, I got time. So I'm done with AGB stars. I'll talk a little bit about supernovae. Of course, when you have a more massive star than the sun, than a few times, maybe 10 times the mass of the sun, they have a very different evolution in that they can keep burning beyond the carbon and oxygen that you see for the lower mass stars. So during the main sequence, you have a supergiant star, an O star or something, it burns hydrogen to helium relatively quickly. becomes a red supergiant. It goes through a whole lot of phases of nuclear burning in its core, where it burns helium to carbon, to oxygen to magnesium, to silicon to iron. Once you get to iron, you can't make any more energy from fusion of iron, because iron has the tightest binding energy. So it can no longer resist gravitational collapse. It collapses and bounces back, and you have an explosion, supernova, and you have a remnant of the iron core that becomes a neutron star or a black hole. Very, very schematically, it's believed that these stars, before they explode, have an onion shell kind of structure. This is highly oversimplified, but the point is that as you go deeper, you reach layers that experience more and more advanced types of nuclear burning. So in these stars, you can expect a very, very wide range of elemental and isotopic compositions throughout. So why do we care about supernova dust to begin with? Well, it's actually been a matter of great discussion in the astronomical community for many years now, and it's been important because dust is observed at very, very high redshift. You can see quasar spectra and see that very, very young galaxies formed early in the universe have a lot of dust. And this was surprising because people thought most of the dust was formed by AGB stars. AGB stars take a fair amount of time, since they're low-mass stars, to evolve. And it appeared that these low-mass or early galaxies had too much dust to explain, so it was suggested that supernova made dust. But it was very hard to see in the Milky Way supernova remnants. And this has changed in recent years with submillimeter astronomy, and Herschel telescope and ALMA are now finding evidence for large amounts of dust in supernova. And this is supernova 1987A. This was a result a couple of years ago. And I can't see, that's 450 microns. Yeah. This very cold dust in the very center of the supernova remnant. So there's clearly dust forming in supernovae. But we've already known this for 20 or 30 years because we have the presolar grains, and some of them clearly came from supernovae. And the biggest proof, what we call the smoking gun, it goes back to 20 years ago. Paper I wrote in last year. Basically, we found that when we measured some of these grains for their calcium isotopes, we found patterns like this. And this is a graphite grain that this is of, and what we found after we measured it was there was a little titanium carbide subgrain. And we measured the calcium isotopes. We found that it had normal calcium 42 and 43 relative to calcium 40, but more than 100 times as much calcium 44. When you see a monoisotopic signature like this, it almost always means radioactive decay. And the parent in this case is titanium 44, which has a half-life of about 60 years and is formed only in supernovae. So this grain had live titanium 44 when it formed. It must have formed in a supernova. Now, titanium 44 is not seen in all the grains, and there's lots of other isotope signatures, but what we know is that all the isotope signatures, or most of them, clearly point towards supernova origins. And I'll get to some examples here. In terms of the oxygen-rich dust, we think all of these grains over here that are sort of complement to these AGB star ones are from supernovae. You have ones that are from almost pure oxygen-16, which are formed in the oxygen-16 rich layers deep inside. But most of the grains we find are oxygen-18 rich. But they have other signatures that clearly point to supernovae, and I'll get to that in a sec. In terms of the silicon carbide, I didn't show this plot before, but the AGB grains on a carbon and nitrogen isotope plot sit up in this region of the plot, and the supernova grains are completely different. They've got less nitrogen-14 and more carbon-12 compared to the AGB grains. In terms of silicon isotopes, again, I didn't show this before, this is silicon carbide. The AGB grains sit near solar, which is 0 on this plot. These are parts per thousand deviations from terrestrial. So minus 1,000 means no silicon 30, and plus 1,000 means twice the solar silicon 30. In any case, we see both silicon 28 poor and silicon 28 rich supernova grains. And we can recognize these from all their different isotope signatures, including the titanium 44 signature. Now, some of you will remember when Ernst Zinner was here as a TÜV fellow about 5 years ago. He gave a talk, and he was very excited about this grain, and we did a bunch of measurements on our lab on this. This is a 30-micron diameter supernova silicon carbide grain. It's actually an aggregate of a whole lot of smaller grains that all have the same isotope composition in terms of silicon and carbon. So it's very easy to prove it's impossible to grow a 30-micron silicon carbide grain in a supernova, but there it is. So it tells us that supernova dust can be very, very big. And there was a paper in Nature last year, I can't remember, or 2 years ago, I can't remember the author, but showing some astronomical evidence for large grains. And they were talking about 5-micron graphite grains in supernova 1987A. So there is some growing astronomical evidence for this as well. So again, going back to this to this schematic idea of a massive star that becomes a supernova, what we can tell is, like I said, from the nuclear burning, we can tell that this layer is going to have had carbon burning and produce oxygen-16. Slightly outside, you're going to have helium burning have made carbon and oxygen-18, and so on, in an envelope that's going to be mostly solar composition with a little bit of mixing of hydrogen burning, and so on. The point is, the grain compositions we see some of these signatures like titanium-44, which is forming very, very deep in the star, and we see helium burning, carbon-12, much farther out. So all the compositions point to that you have to have contributions from different cells and pointing to heterogeneous mixing. You can't just mix all this and get the composition. So this is one of the key results of this study, of these studies. And this is just an example now. This is for a couple of the oxide grains. And basically the open symbols are the grain, and this is a mixing model showing you can simultaneously explain an awful lot of the measured points in a single grain with a single mixing of a supernova model. So this provides further evidence that these form from supernovae, but they have to have this mixing. Well, is this mixing plausible? And the answer is yes and no. We know from both observations and theory there should be mixing in supernova. And this is an X-ray image of Cassiopeia A supernova remnant, where the three colors are three different elements. And you can see this red is silicon that's coming from deep inside and jets coming outside the outer layers. This is a very old 2D hydrodynamical simulation. I should find there's much more sophisticated ones now, but they show the same thing, that you can get these Rayleigh-Taylor and other hydrodynamic instabilities that mix material. But the problem is that observations in theory neither can probe the microscopic scale of mixing that we're seeing with the grains. So we're coming at the same issue from different ends, and we're a long way from meeting.
Yeah, Larry, how do you see this disentangle the nuclear synthesis that takes place before the explosion with what takes place during the explosion?
That's a very good question, and I would say in some cases it's easy, and in other cases it's not. And it's actually something that Nan and I are working a lot on, and I'll get to that briefly in a second. But some signatures are clearly pre-supernova, some are clearly post-supernova, like the titanium-44. You don't make that before the star. But there's a lot of signatures that could be before or after, and that's what we're trying to piece out, is because it's important for understanding what material went into the grains. As I mentioned before, the supernova graphites, the graphite grains have these subgrains, and in fact detailed work mainly by the Washington University group has found that when you look in detail at some of these subgrains, this is now 50 nanometer scale bar. This has an amorphous sputtered rim. Probably this grain of titanium carbide condensed on its own in the supernova was then hit with high energy radiation, radiation to sputter the outside before it got captured by the growing graphite. So there's incredible detail of the dust, physical chemistry of dust growth in supernovae by studying these things. And these observations are way in advance, way farther than anything can be done theoretically at this point, but it's clear that these kind of observations could be extremely valuable for understanding how dust forms in supernova. And this is work I did with a graduate student from WashU a couple years ago who came here for a few weeks. And this is a very interesting supernova grain, graphite grain. This is a slice through it from a TM. And it has this very compact sort of amorphous carbon core surrounded by these layers of graphitized carbon. And this is an oxygen isotope map we did with the nanosims. And what we could find is that one of these layers of carbon had much more oxygen-18 than the other layers. So as this carbon is accreting, the grain is probably moving through gas that's changing in its composition, has changed composition. So this is kind of a time capsule of either time capsule or some sort of gradient through the gas of a supernova ejecta. And these are X-ray absorption spectra we did of this, and I don't want to get into any details, just to show that, we're trying to apply as many techniques as we can in the hope that we can get useful astrophysical information. And this is kind of interesting, potentially, because this is the kind of thing that eventually one might be able to do astronomically, fly a high-resolution X-ray, soft X-ray telescope that could actually probe this kind of structure. It's not feasible now, but it probably will be eventually. This is a very important result from our group, simultaneously from the University of Chicago and from Li Ping, Chin, and Rick, and Connell and me here. A few years ago, we discovered that there are these extremely chromium-54 rich grains in the Orgay meteorite. And these are almost certainly a supernova signature, supernova grain. And they're tiny. These are like 100 nanometers across or 80 nanometers across. So I showed the bonanza grain before that was huge. Supernova also make very, very small grains. And these grains are important for meteoritics as well, because they probably explain differences in the bulk composition of chromium in different classes of meteorites. So I wanted to briefly talk about Novae. As I said earlier, Novae are thought to be a source of some of these grains. For those of you who don't know, Novae are phenomena that occur in binary star systems where you have a white dwarf close to a secondary star that's either a main sequence or a red giant star. They're so close that material from the larger star accretes onto the white dwarf, and if the timing and everything is right, periodically the hydrogen builds up and catches nuclear fire, and you have a little explosion. Not a little explosion, little compared to a supernova, but I still wouldn't want to be near it. And this is characterized by very, very high temperature hydrogen burning. It's what's called explosive hydrogen burning. And at these, you produce very, very large amounts of carbon-13, oxygen-17, oxygen-18, produce some important radioactive isotopes. And it can also affect nucleosynthesis, maybe up to sulfur. But it's really a light element thing, and it's distinct from the nucleosynthesis that's standardly predicted in AGB stars and supernovae. So many years ago now, we published a paper suggesting that these grains that have very low carbon 12 to 13 and nitrogen 14 to 15 were from Novae. In 2004, I measured one of these grains and found that all the other isotope signatures looked very much like a supernova grain, which immediately made this more complicated because it looked like it came from a supernova, but it had this isotope signature that the supernova models did not predict. So more recently, and this is a paper that just was published this month in the Astrophysical Journal by Nan, who did this work last year. She found 14 new of these Nova grains with these very low carbon 12 to 13 and nitrogen 14 to 15 ratios. But she was able to measure a lot more isotope systems in them than we were able to with the previous data set, including titanium and aluminum, magnesium, and sulfur. And what she found is that for many of these grains, they require a supernova origin, but not a standard supernova. And we worked with Marco Pignatari, who's a supernova modeler at the University of Hull now in England, and he basically has a model that during the supernova, you can inject hydrogen from outside, from the hydrogen shell into the helium shell that then explodes. It burns explosively, so you basically make a nova-type explosive hydrogen burning in the helium-burning shell of the supernova. And when you do this, you can actually explain a lot of the isotope signatures quantitatively. So this seems to be evidence that this kind of supernova can occur. There's no other, we have not found any other plausible explanation for the grains. They certainly are not from Novae. A few of them could be from Novae, but it's ambiguous. And we may prefer a supernova, but it's hard to say at this point. The point is, we don't have direct evidence that we absolutely have any silicon carbide grains from a Novae. We before thought we had a very tiny number, and now we think a tiny number might have gone to 0. In any case, it's much less than 1% of the grains. On the other hand, the oxygen-rich grains, there's this population of grains that have a very, very high oxygen 17 to 16 ratio, much higher than can be explained by the other stellar sources. This is, again, a sign of nova nucleosynthesis. They also have magnesium and silicon anomalies consistent with Novae, and perhaps these really are from Novae, and we're hoping to find new signatures that might really pin this down. So Novae at this point are ambiguous. And I'm pretty much out of time. Oh, very briefly, I want to talk about this, which is on this carbon and nitrogen plot of silicon carbide. You see there's this whole population of grains plotted as blue diamonds on here that have very low carbon 12 to 13 and a very wide range of nitrogen isotopes, but much higher than these grains we called from Novae. These were called, well, they were first called A grains and B grains, but for many, many years now they're just called A and B grains. I could get into the history of nomenclature. It's just as crazy as it is in every other field of science. The point is that we don't understand the origin of these grains. They have very similar carbon 12 to 13 ratios to a class of star called J stars, which are observed. They're carbon-rich giant stars, but their origin is not understood. Some of their isotope signatures suggest they might be what's called a born-again AGB star, which is essentially an AGB star that has pretty much evolved to the planetary nebula stage and has one last thermal pulse that mixes material into the nebula. And there's a handful of these have been observed in the galaxy, and there's some reason to think these grains. Some people have suggested they're from Novae, and there's some possible evidence for that. So these are unknown, and part of the problem is we don't have that much data, good data for multi-element data for these, and especially for trace elements that may be diagnostic of different nucleosynthetic processes. So I wanted to point out that Another thing that Nan's been doing that's very, very exciting is working with Steely over in the geophysical lab to do Raman on silicon carbide grains. And the point is that that there's there's a couple well-defined features, and this is from amorphous carbon, but this peak here is from the silicon carbide itself, and these are two different silicon carbide grains that she measured, and you can see they're pretty much at the same value here. But what she did was measure Raman for a lot of these grains and then correlate them to the measured carbon isotope ratio we see from the nanosims. And what you see is an actual correlation with the position of this peak with the carbon-12 to carbon-13 ratio. And so these are these A and B grains that have the low carbon-12 to 13. And the point is that this seems to be a non-destructive way to find more of these grains, which is really exciting because for most of them, you want to find these rare grains. You actually have to measure them by the SIMS to find them, and you're throwing away atoms while you just find them before you can do anything else. So if we can really, this is a really exciting way of doing isotope measurements by Raman spectroscopy. And so she has a paper she's waiting for me to read, so we can submit it. And I'll get to it very, very soon. I was going to talk a little bit about this, but I think I'm out of time. Well, I'll give it a second. You guys can be patient. There's one last thing I want to talk about, and that's the way we used presolar grains not to probe what happened before, but what happened during the formation of the solar system. And coming back to this idea of what the solar system looked like when it was very, very young, we know that we we find presolar grains both in cometary materials and asteroidal material, meteorites and cometary interplanetary dust particles, as well as samples brought back by the Stardust mission from Comet Build 2. And we know that the asteroids form much closer in to the sun than the comets. And the comets are very, very primitive, we think, or have experienced quite little processing on their parent bodies, where asteroids have seen quite a range of processing. Some have been heated, some have been completely altered by water, where their original minerals have completely turned into clays and things. And the point is that it's been recognized that presolar grains are very sensitive to some of these processes. So we can use their abundances as tracers of processes in the solar's early disk and on their parent planetary bodies, asteroids and comets. And this was something that Gemma Davidson was working on while she was here. Well, this was actually work she did for her thesis, which was to look at the silicon carbide abundance in different classes of chondrites. And what she found was, these are all mostly carbonaceous chondrites, found that silicon carbide, which is not very sensitive to things like aqueous alteration, to this water processing, is very constant abundance. It's 30 parts per million or so of all these different types of meteorites, which tells us that where the meteorite matrix formed in the inner solar system was very well mixed in terms of presolar grains. When you look at more heated meteorites, you see the silicon carbide go away because it gets oxidized when you gets heated to many hundreds of degrees. But for the primitive ones, it's like this. When we look at the oxygen anomalous grains, we see a very different story. What we see is that in the interplanetary dust particles that are from comets, we see presolar silicates can range up to 1% of the particle. Whereas these different classes of chondrites, the most primitive ones seem to be a few hundred parts per million, but some meteorites you can actually, I don't have all the data on here, get down to 10 ppm, 20 ppm. So these can be very, very sensitive tracers of the processing that occurred in their parent bodies. And we're trying to correlate this with the actual mineralogy and petrology of the meteorite, so we can actually say this part of the meteorite got heated more than this or whatever. So this requires very, very detailed work, but it's potentially very valuable. And I think that's probably all I had to say. So conclusions, a lot of motherhood statements about how great presolar grains are and important they are, and they tell us everything. And I want to really thank Connell, who's been my, I guess, speaker today? No. Okay, then I won't say nice things about him. No, no, as Alan said, Connell was a postdoc at Washington University when I started as a grad student. I shared an office with him for my first day of grad school, so I've been tied to the hip for Connell for my entire professional career, and I owe a great deal to him, and he's still a big part of all of this work. Had fabulous postdocs over the last few years, Gemma and Aki and Nan, and Steely's being enormously helpful with his Raman work. Of course, close collaborations with Rhonda at the Naval Research Lab, Frank, another former Carnegie fellow, still working with him, now he's back at WashU, and working with Marco Pignatari and Maria Lugaro, who are two world-class nuclear astrophysics theorists to better understand things. And I'm starting to make new logos for various aspects. So there's the official Carnegie NanoSims logo. I'm probably breaking some rule, but Don't tell Matt. Oh wait, this is live stream. Oh well. Anyway, thanks. I'll take any questions.
Wow, that's a fast ride. Okay. Some questions. Alicia.
So, can you tell, or do you not see any type 1A supernova or type 1 supernova grains?
No, we don't. And there was a paper by Dave Arnett and Don Clayton, circa 2000, 2002, something like that, that suggested that some of the supernova, the silicon carbide X grains, could be from type 1A. But that's been ruled out by subsequent measurements of the trace elements, like the molybdenum and zirconium, which show a neutron signature that you can only make in a type 2 supernova. So one thing, I don't think there's any evidence that type 1A supernovae make any dust. But maybe you can...
Well, I don't know. I mean, there have been, recent observations, including people like Josh Simon at the observatories, that at least show gas in the vicinity of the supernova.
Yeah.
And so you think...
And maybe some of the grain, I was talking about the main population, but there are oddballs. We have grains that just sit over here on the diagram, and we don't have any idea what they are, and it could be that. It's also, the chemistry could be very strange in a type 1A supernova, depending, that you're ejecting gas that might be pure, basically pure iron with some other heavy elements, and almost essentially no hydrogen or oxygen, maybe a little oxygen, a little silicon, but...
I was wondering if you could explain the hydrogen injection of those.
No, because I don't think there's enough hydrogen around. I mean, the key thing with the type 1A is you don't really have...
At the last moment, you're still dumping hydrogen onto the supernova.
It's a very good question. The people who model the nucleosynthesis system type 1A supernovae aren't looking at that level of detail because they're trying to figure out how much iron they make and also trying to understand physically what the hell is a type 1A supernova, because we don't really know that. But it's a good question, and the few times people have tried to directly relate the models to the grains, we haven't found a match, but we can't rule it out. Similarly with Wolf-Rayet stars, there's some isotope signatures, which, these are very, very massive pre-supernova stars, 50 solar masses, 30, 60 solar mass stars. And some grains have been suggested to come from these, but there's no hard proof, I would say, at this point. Okay.
So I mean, you made a good argument as an interaction between the observations and so all those before the pre-solar grain was observed, is there the predictions and how much was based on the observation developed model, and how much? And my really follow-up question is there anything else you were looking for, based on predictions?
Yes, so we're looking for anything we can measure, and and there are predictions. Next week, Nan and I are taking a handful of these silicon carbide grains from supernovae to Manchester in the UK, where they have a unique resonance ionization mass spectrometer that's designed solely to measure xenon. And we want to measure see if there is any xenon in these grains, and if so, what's its isotopic composition. And there are predictions for xenon isotopes in various shells of the supernova. So if we see it, we can compare directly with those models. So that's an example of one of these things we would do. Going back to the beginning of your question, yeah, there were many predictions for the isotopic compositions of these various sources and so on. And part of the reason we were able to make progress pretty quickly once the grains were found was that there was an existing set of models that we could compare the data to. And I didn't talk about all the cases where there are isotopes we measure that are in complete violent disagreement with the models that we don't understand at all. So this new instrument in Chicago, Chile, this new RIMS instrument, they just reported the first set of data from that for iron isotopes for silicon carbide grains, and they find very little variation in iron compared to what we would expect, and it's not clear why. But again, I just saw this data at a conference last month, and it's brand new instrument, brand new data. I don't know if it's going to make it all the way to publication.
Well, I'm probably missing something really simple, but how do all these grains that clearly did not form in the solar system ended up here?
Because the solar system formed from a pre-existing cloud that had gas and dust in it. So the solar system doesn't form out of nothing. It forms from a pre-existing thing in the galaxy. And that thing is a cloud of gas and dust, and some of that dust is coming from these stars. So it just happened to be part of the very, very start. These grains were part of the very starting materials of the solar system. They probably weren't a major part, but they were some part, and some of them have survived. that make sense?
Well, so following on John and Sergey's question, can you say anything systematic about the relative ages of these groups and how they're delivered to the solar system, you know, looking beyond the assembly? Because to the uninitiated, it looks like you're just looking for stuff that's out there, but there ought to be some systematic age variation in some of these grains, I would think, given where they were and you know, how far away they were.
Oops, hold on. So I have one backup slide. Dang. It's very, this kind of gets at what you're saying.
Yeah.
This would be a holy grail of this research if we could really absolutely determine the ages of these grains. All we know is that they were present 4.5 billion years ago.
Right.
We don't know how long between their formation time and 4.5 billion years.
Could they be 9 billion years old?
Probably not, and these are the only existing data for this. And this is work Frank Gingard did for his PhD thesis, as well as work from Uli Ott in Mainz. And Frank looked at some very large silicon carbide grains, looked at lithium isotopes, which are affected by nuclear spallation as these things flew through the interstellar medium. And he estimated ages for them from a few tens of millions to a few hundred millions of years, which is kind of consistent with theory, which expects these grains last for 500 million to 1 billion years. This is a very unrepresentative sample, and these are very difficult. It's, of course, the original development of the resonance ionization, what was hoped for was they'd find enough uranium to actually do some absolute ages. It turns out uranium doesn't seem to be present in these grains. So this is very, very, very difficult. I'm sure as technical advances go, we'll figure out a way to do it. But for now, all we know is these grains were around before the formation of the sun. But they could have all formed 10 million years. You know, probably not 10 million, but they all could have been within 100 million years of the formation of the solar system. There's no way to correlate their age with anything else at this point.
So in relation to that question and to your question, of course, Miriam Tellis's talk a couple of weeks ago, she pointed out that there may be evidence that is perhaps still correct that there was a live iron-60 found in some of the most primitive components. And if that's true, then the iron-60 probably was synthesized in a core collapse supernova, maybe no more than 1 million years or so before the formation of the first refractory solid. So that would be pretty quickly formed, as well as these much more ancient, possibly billion-year-old grains. So if you believe that, then you have to have some way of having these things synthesized in supernova and then transported across the interstellar medium, and perhaps triggering the collapse of a dense cloud core, so it sweep things up and bring in the freshly synthesized isotopes as well as the older stuff. Sandy Kaiser and I have been working on these models for many years, and so we have some theoretical understanding of how that happens. The question I have that's related to that is, as you point out, there are observations of supernova-derived grains that range from sub-micron, 100 nanometer scale to maybe 10 microns in size. And such grains behave very differently in terms of a shock wave, trying to get them injected into a target cloud. If they're really big buckshot size, they'll punch right through the shock wave and get ejected. If they're little tiny guys, then they kind of have to come in through instabilities. So we see evidence for both of them, apparently. And the real question for my mind is, well, it's the amount of them. The big guys are easiest to see. Do you have any feeling for what fraction of them are really are greater than a micron versus what fraction in terms of mass fraction are submicrons?
The vast majority of grains are submicron from both the supernova and the AGB stars. But you're getting at something that I didn't really say, which is with the AGB star grains, we can actually estimate, and this is something Connell started doing a long time ago, you can make estimates of the number of stars that contributed, and it was probably tens to hundreds of individual stars that did it. With supernovae, that's much more difficult. The fundamental question that gets to you is, could all of these supernova grains have been made in one supernova? Or are they also sampling a whole lot of supernovae that just happen to be around there? And we made the argument in this paper with the chromium-54 that perhaps these little tiny chromium-54 rich grains were all injected by a supernova at the formation of the solar system. And the reason is there seems to be evidence that they're heterogeneously distributed in the solar system, and that might be easier to do if you've injected them nearby rather than be pre-mixed in a molecular cloud. But there's no proof for it. I just like the idea. And the problem with pinning this down is that supernovae are so heterogeneous. You have all these different signatures. So you can make grains with extremely different compositions in the same supernova. You can't do that in an AGB star, but in a supernova you could. So in principle, you could make a huge range of the compositions we see in a single star. And ultimately, I hope we can really pin this down and say, yeah, these grains were injected by a supernova that made iron-60 and aluminum-26. But we're not there yet, but we're working on it.
Okay, last question,
Well, I
Lisa?
was gonna just comment that I think it would be very unlikely to find grains that predate the solar system by billions of
Yeah.
years, right? Because the molecular cloud assembly time is
Right.
probably less than 100 million years.
And the models suggest that grains don't live that long, that they eventually get hit by a supernova shock and get destroyed. I gave an astronomy group meeting talk a couple of years ago where I argued that they're very, very short lifetimes, that they all formed 10 million years before. But I don't actually believe it, but it explains some of the data. That's why I haven't written the paper yet, because it's hard for me to write a forceful argument for something I don't actually believe.
Okay, so Larry will be around for another 20, 30 years or so. Let's thank Larry again.
Thank you. Yeah. No, 6 years. No, I'm very
So given that,
I trust you know how to trim this off.
Well, you have a really old grain. It's just the probability is getting really low. And your probability of hitting a shock in the interstellar medium after 10 or 20 or 30 million years is like 1, right? So, but, you know, if you're looking at a million grains, like, you know, you could find one that hasn't experienced a shock. I mean, there's still a big disagreement amongst astronomers and critics, I think, about the shock, prevalence of shocks. In the sense that,
it just always, I mean, I heard Larry's talk now for all these
Yeah.
years, and the frustrating thing about it is you want to connect it to a physical model.